Caulcrick. I'm a PhD student from the Biomechatronics Lab of Imperial College London. And today I'm going to be talking about muscle activity-based model predictive control for robotic rehabilitation. So rehabilitation robots for stroke patients are attracting great attention as an alternative or a supplement to existing rehabilitation activities. So a great example of this is the ExoGT from Exoskeleton. This exoskeleton has actually been deployed in over 30 countries. Active-assisted exercise is a well-known and useful physiotherapy method used by physiotherapists, and it essentially involves applying assistance as needed for patients who do not have sufficient muscle strength to complete a particular rehabilitation task. Implementing this using robots is a challenge, and we aim to do so in a knee exoskeleton. So we propose a muscle activity-based optimal control framework. Our controller adjusts the human effort contribution during a rehabilitation task using muscle activation signals as part of the model predictive control cost function. We use the useful constrained optimization features of MPC to make sure that our system operates safely, prevents patient discomfort, and protects the system hardware. So our controller is applied to a seated 1 degree of freedom knee exoskeleton. It uses the following human exoskeleton model. In this model, the theta refers to the knee joint angle. Tau E is the exoskeleton torque, and tau H is the human torque. So our human torque is estimated from muscle activity signals, and we estimate this human torque using a linear antagonistic model. Our MPC computes the optimal input by minimizing this cost function. So here, W theta is our tracking error weight, W tau is our input torque weight, and M is our novel mode function. So this function adjusts the weight, essentially changing the gain using a fuzzy inference system. And the input to this fuzzy inference system is the exoskeleton torque at the current time and the estimated human torque at the current time. So this is what our mode function looks like. P is the penalty cost, and lambda is the membership score for both the assistance and resistance mode. So in our assistance mode, our gain is gently reduced in order to achieve a human-robot interaction equilibrium for the rehabilitation task, and R is our resistance. So this greatly penalizes the gain, essentially halting the process for wearer safety. Our fuzzy inference rules are fairly simple, and they're based around N and P membership functions, which are for negative and positive. And the way it works is that if the exoskeleton torque and the estimated human torque are working together, then our lambda A tends towards 1, and if they're working against each other, then our lambda R tends towards 1. Our controller works in simulations, so we tested it on the eCozy exoskeleton. This is without the mode control, so the controller closely follows a sinusoidal trajectory, and this is with the human leg relaxed. We recorded data during the MPC for 5 human effort types, and these represent all the different types of assistance and resistance behaviors. So we use this data to tune our muscle filters, our fuzzy inference system, and our human torque estimation model. Early results suggest that mode switching can be achieved using these muscle activity signals. The controller followed the trajectory well, but the gain changes here were sudden when flicking between modes. This isn't the behavior we were hoping for, so we want to improve this by further tuning our fuzzy inference system parameters, and hopefully we'll be able to achieve smooth mode switching in the future. As well as the fuzzy inference system parameters, we hope to improve the human torque estimation accuracy, possibly by using a Hill muscle model. And also, we want to control an exoskeleton for rehabilitation during upright walking by adapting the model with a passive hip joint, and hopefully testing in the future on stroke patients in clinics. Thank you all for listening. I would also like to thank the EPSRC and McLaren Applied Technologies for their support.
Okay, we got several minutes for questions. I'm going to go ahead and start with one. How do you choose theta desired, the reference trajectory?
So at the moment, the reference trajectory is arbitrary, so it's just following a predetermined path. But this would be determined by the physiotherapist just for whatever an appropriate exercise is in order to regain mobility in a particular part of the body.
Do you think there's any way to wrap that into your optimization?
Yeah, absolutely. So one feature that I haven't mentioned here is for the resistant mode, which is where the patient is resisting against the exercise. We plan to either reduce the gradient of the trajectory change or halt it completely, and that can be incorporated fairly easily adaptively into the process. Also, you could sense during the assisted phase that a patient's doing better than expected and possibly speed up the oscillatory process, for example.
Great. Any others? Yes.
Hi, Patrick Frank from Stanford. We hear often in rehabilitation with participants in like the locomat that they'll disengage. They'll just be going through the motions and let the robot do the work.
Yeah.
And these paradigms where the exoskeleton is capable of following that desired trajectory with the participant not applying any force, how do you try to maintain user interaction and effort?
I think that would be something that would fall partly under the responsibility of the therapist. So you'd have to have an appropriate setup where the patient is engaged, but also if the patient does completely disengage or, for example, through fatigue, stops interacting with the robot, then the default process for the robot is to just use the default gain, which would essentially mean that the robot's in charge and the robot's going through the rehabilitation process without any human effort contribution.
That was my question.
Yes. Vince from Stanford. Have you considered sort of like a more like game-like reward thing where instead of, their responsibility is to try and resist this constant trajectory, like you detect whether or not they're doing better, but instead of like when they're doing better, instead of resisting them more, you like reward them through some way?
So I'd say that the aim of what we're going for isn't necessarily the trajectory at the moment. What we're looking for is appropriate human-robot interaction. So what we can do by tuning parameters is encourage patients to contribute more effort to the process, and hopefully through them sensing that they're contributing to the process and through them achieving greater motion than they would be able to on their own, hopefully that will provide a sort of psychological reward and be beneficial in the process.
I have a question about your efforts to tune up the fuzzy inference system.
Yeah.
So sometimes fuzzy systems in general can sort of blend modes to do an in-between thing. Is that something that you think could be useful for smoothing out these transitions or making them fewer?
Yeah, absolutely. So the implementation and testing that I've done so far wasn't successful in the sense that the mode transitions weren't smooth and it wasn't transitioning smoothly between the modes. But I realised that with better tuning and possibly a different fuzzy inference approach, this should be achievable, and it's something that we hope to do in the future. Yeah.
Okay, very good. We've got time for one last one while they swap if there's another question. And if not, let's thank him again.